Okay, so welcome to the physics lab, welcome to the darkness that this is, and what I've got set up here is a laser on a little magnetic whiteboard, and what you can see is we've created a ray of light. So we've got a singular ray of light that's coming out and going in straight lines, and because that's what rays of light do, so they go in straight lines. Now, one of the curious things that people notice, and it was observed by the ancient Greeks, but took them ages to try and work out what the relationship was to notice what happens to light when it changes medium. Okay, the medium is what it's travelling through. At the moment, it's travelling through the air, which is pretty enough close to a vacuum for light, so 300 million meters per second. And the question becomes, what happens if it enters a different material? If it starts to travel through something different. And so what I've got here, it's probably hard to say, this is a perspex block. So I'm now going to let the light travel through a perspex block. And at this point, it doesn't appear to really as much as anything is happening. But what happens when we start travelling at an angle? Now, what you probably hopefully can see is there's our ray of light coming out, hits the block, and then it changes direction. The angle has altered, okay, so it's moving a slightly different direction, and then when it exits, it's back to its original, like parallel to its original direction, but it is shifted. It's been moved in a certain way. So someone observing this beam of light is not going to see something where it truly is. It's going to be in a shifted position. And this phenomenon is called refraction. And it's what happens whenever light or other electromagnetic waves move from one medium to another. And that happens because, although in the air this light can travel at 300 million meters per second, through a perspex block, it can't. It's more optically dense, fundamentally because it is more dense, which means that the light can't travel through this at the same speed. It slows down in the same way that you would if you start running through the air and then I start asking you to run through a perspex block. Hopefully you're going to realize, yeah, you're going to be slower going through this. And so when we try and move through it, we have a change in direction. Now this was something that was observed. Rays of light. This was observed by the ancient Greeks, but they never really were able to explain it. They could never come up with a rule that enabled them to predict how much a ray of light would bend and change direction. But it's noticeable and it's there. And the reason it's important comes up because refraction is something that's all around you. In fact, what you're using to look at this right now is something that uses it. So I'm going to put up a model of the eye. And inside the eye, you have a lens. So I've got a lens, which is same material. Pop it up there. And the aim of this is to make sure that we always get rays of light striking at the same thing. So at the start of in front of your eye is a lens, and what it will do is it's designed to focus rays of light so they operate on the same place. So as I move this ray of light upwards, what we find is that no matter the kind of angle, no matter how high up these rays of light are, what I'm getting is I'm getting a focus essentially to there. It's a bit hard because it's not quite a thing, but if my finger is there, we've got a ray of light, we can see that. And as I move the ray of light, the ray box down, I still get the focal point on that part of the retina. And so the aim of lenses in the eye is to focus it. So refraction is what enables you to see it. It's because the speed of light through the material that makes up your lens is different to the speed of light in the air. If that wasn't the case, it wouldn't be possible to focus anything, and you'd have very, very blurry vision. And so that is one of the sort of common things. Any some optical system where we've got to focus rays of light to a particular point, that all happens and is able to happen because of refraction, because of the changes of speed that occur when light moves from one material to another, which leads to a change in direction. And so what we're going to do is to try and see if we can see the relationship between the angles that are going in and the angles that are coming out, or the angle of incidence and the angle of refraction. So I'm going to show you the setup for the experiment. Okay, so this is an example of the experiment that you would have done if you were in lessons, but we're going to do it using a simulation. So it's just to show you how you do this practically. Oh, the lights have gone off, that's exciting. So what you use is you have a thing called a ray box, which is going to produce a ray. You can see it just there. A perspex block, which is what we investigate. We send the light through it. You need a protractor to measure an angle, and you use a ruler. Okay, and then normally what would happen is turn the lights off. So I'm going to turn the lights off. Hooray! Lights are off. And so what you can see there is this is beautiful. There is our ray coming in. It is refracting here, and then it's coming out. And what we're interested in is what's going on as it changes material. So in order to do this and to take these measurements, here's what we have to do. We draw around the block. Okay, so we have a drawing around the block, and we have to mark the entrance and exit points. And once we have that, we can turn the lights back on. So we can remove the block, and we now have the ability to connect things up. We have our movement here. We have the ray of light which was coming out along this line. And then because we know that things collect that light was travelling in a straight line inside the block, we saw it, we can connect these two up like so. And so this is the path that the ray of light was taking. And what I'm interested in is what is happening here. And I have to define a few things. So we have to then draw what we call the normal, which is a word that simply just means at 90 degrees to. And we have this, which is called our angle of incidence. And we have this, our angle of refraction. At which point we then get the protractor, start taking measurements. So lining this up, 0 through, I'm getting that as being about 40 degrees. And then I've got my angle of refraction, which I am getting as being, make sure that's on the right thing. This angle here, 0, 20, 5, 6, 27 degrees. And so what I can do is I can repeat that at various different things. So I can send in a second ray of light, at say a different angle and then more, and I can collect a large number of angles of incidence and angles of refraction. So that's what I'm going to do. You don't have to sit there and watch it, but there'll be a little table of the measurements that I've taken so you can see it, and an opportunity for you to repeat using the simulation. Now what's interesting as well, just to be clear, is that you can do this with anything that stuff can travel through. You can even do it with water. So I can put water in, and I can do the same experiment. Might need to turn this over. But I can do the same experiment, same idea. Turn the lights off. Draw around my much bigger box this time. Okay, mark the ray of light going in. Mark the ray of light coming out. And then let's do the same thing. Move this to one side. You can see the path that the ray of light would have taken had there not been any water in there. It would have just gone along this line, but I can do the same thing. There's the ray of light going in. I've got my ray of light coming out. Connect the two according to what they went through in the interim, and obviously the lights now go off because that's what happens when you're one of the only people in the lab. Wave around, excellent. Back on, and draw the normal. And let's measure some angles. So there is our angle of incidence, which is this time 40, 41, that's 42, yeah, it's about 42 degrees. It's hard to be much more accurate than that because I'm limited by the resolution of my protractor. And I can go the other way. And I get this angle here, which is my angle of refraction. For a fraction, sorry, and this time this is 30 degrees. And that would be for water. And so what I'm going to do is I'm going to repeat that several times, collect up some results, and you can see what the results are that I have obtained. And then we'll see whether or not we can see, you know, how this angle here can relate to this angle here. So, having seen it done in a lab, how are you going to do it from the comfort of your own home? Well, it's the good old PhET simulator. So, here is our sort of like intro, and this is where you're going to take your readings. So, you're able to determine the difference between the medium that you're in, which is the top box, because that's where our laser is, and the medium you're going into, which is the bottom one. At the moment it's water. No, let's turn it to glass, which is pretty much the same as Perspex. You can ignore the other things. You just need to worry about the selection of these things here. So glass on. And what you're going to do is to collect a series of results. So it's not just about collecting one result, it's about collecting a series. So what we can have is we have a laser that we can move. We've got our angles of incidence, angles of and angle of refraction. We've got the normal is drawn. It's helpful. And so what we can do is we can bring out the protractor, which is a great one. It's a sort of 360 protractor, and we can put it at the place where we're striking. So we have that there. And we can take some measurements. So, so we can take a series of measurements by moving the laser. So let's say if I move the laser here. So my angle of incidence is 30 degrees. What is my angle of refraction, which is what I measure from the normal the other way. Reading that, I would read that as about 19 degrees would be my best read of that. And what you can do is you can take it at a series of readings. So we can do that at 60, we could do it even at sort of 80 degrees, and we can take these various different readings for these things. So we're going to do that once, and then what I want you to do is to change the material you're going into, so you can change it into water, and repeat. And you're looking to get about 6 readings for each one. And that's what we're going to get for this thing here. Don't know what these mystery ones are. Mystery. Ooh. Oh, might come. Okay, so having collected your results, we're now going to see about what it is that we can do with them and the conclusions that hopefully you can draw. So the first thing is that when a ray of light goes into a more dense medium, so from air into glass, what we get is the ray bends towards the normal. And the reason that is that the angle of incidence is greater than the angle of refraction. And that happens because of a change in speed. So as far as the ancient Greeks were able to ever work out, though, they could only ever say that. They could only ever really say that when a ray of light moves to a more dense medium, it refracts towards the normal. Okay, and the opposite happens when it comes out. So that means that, you know, this ray that's coming out is bending away from the normal. So you've got this refracting towards, refracting away from the normal. But so that just told you that angle of incidence was greater than the angle of refraction, but they never knew anything like that. However, a guy called Willebrord Snell in 1621 came upon how he could actually link together those two equations in order to see something's constant. In physics, to make a prediction, you've got to be able to say you've got to be able to relate two things in a way that's better than just saying one number's bigger than another. It doesn't allow you to make a prediction. So Snell defined something called the refractive index, which is a constant for a material. So the amount of refraction depends on the refractive index of the material. And this is found through what we call Snell's law. And Snell's law says that the refractive index is equal to sine of the angle of incidence over the sine of the angle of refraction. Now, it's a bit weird for those of you mathematically minded. The fact sort of the sine comes about because you're starting to deal with sort of ratios of how far along something goes and how far down things go. So you can form these little triangles based on, so you've got this sort of triangular methodology, and so it's it's the sines of angles that are related, not the angles directly in themselves, because of the way that the light is travelling. Now this is written as a letter form. Refractive index, because it's a ratio of two things, it doesn't have any units, it's a number, so it gets called this symbol of n is equal to sine I over sine r. And that is the equation that we use. So as an example, okay, one of the sets of data I took was that I took a set of data from water, which had so from my set of water, as you know, sorry, I'll do my perspex. So Mr. Tickner measured I went back and checked the video. I measured 40 degrees for I, and I measured 27 degrees for R for perspex. Okay, and I can therefore say, well, what is N in that case? What is my refractive index of perspex? So I would say that my refractive index is equal to sine of 40 over sine of 27, sine 40 over sine 27, and I get 1.42. That's my value of the refractive index of perspex. Now, it does tell us a couple of other things, which I'll cover at a later date. Is that one and only result good enough? No, because there's error in my measurement. You saw me. I didn't do it it didn't take very long to do it, but maybe my protractor wasn't aligned perfectly. The thickness of the ray of light I was using and the thickness of the pen that I was using to draw things with. So I can't be like 100% sure about these two angles. And that's why, much like you've just done, the best way to do it is to do it over multiple values. So a range of values. So you don't just fire it in at one angle. You then try firing it in at another angle. And then again. And you take these measurements repeatedly, which is what you've done. So what I want you to do now is to go back to your results. And for each of the 6 results you've taken for water and for glass, I want you to work out the refractive index. So find N for each value or each measurement. And then take an average. And so what you should have is a refractive index of water and a refractive index of of glass, and hopefully you should notice that they might be the same number that appeared on the simulation.